Okay, so now we get to talk about our continuously compounded interest formula. And this is where the number of times we compound per year gets so big that it just turns into infinity. Instead of like compounding it every month or every day or every hour or every minute or every second, we just say we're compounding it always. So the interest is always adding back in and earning more interest. Okay, so that's the idea behind it, and it comes from the idea of what the number e is, which we're going to talk about. So here's our formula. Instead of p times 1 plus r over n to the nt power, this simplifies to p to the rt. So notice there's no more n, and that's because we're not compounding a certain number of times per year. It's just always compounding, and that is incorporated into the number e. So let's explore e a little bit here. So e is approximately 1 plus 1 over n to the nth power. So you can see that's the part of the equation we removed and replaced with e. Because as we use bigger and bigger numbers for n, it ends up converging onto a certain number, which we call e. So if you want to play around with this with me a little bit, first of all, your calculator, again, will have the number e in it somewhere, usually associated with the button that you use for natural log. It might be a shift key to get to the e or to get to the natural log, but they're usually put together somewhere on the calculator. So your calculator might give you this number right here if you try typing in just an e or an e to the first power or something like that. And I'm just writing down as many decimal points as my calculator gave me, which is quite a few more than we actually need for a fairly accurate answer. There you go. So let's explore this definition of e a little bit as n approaches infinity. So for larger and larger values of n. So if we play around with this a little bit, like if we let n equal 1, so that's compounded once per year, then we would do 1 plus 1 over 1 to the first power, and that would just give us 2, right? So if we were compounding annually, then the stuff in the parentheses turns into just this value here times 3, basically. Okay, what if we compound semi-annually? Then that will be 1 plus 1/2 to the second power. So if you go ahead and put that in your calculator, you'll see that we start getting a little bit bigger value here. Okay, what if we compound quarterly? Oh, I didn't even write down that number, so I'm going to have to calculate it because that one's not on my paper. So quarterly would be 1 plus 1 over 4 to the 4th power. Let me throw that in my calculator really fast. And I get 2.44. Okay, what if we do monthly? So 12. So 1 plus 1 over 12 to the 12th power. So 1 plus 1 over 12. And then take that to the 12th power. And we get 2.61. So if we just keep going into bigger and bigger numbers, just, I don't know, we could do daily if you want, 365, or we could just pick whatever random numbers, big numbers we want to plug in. It doesn't have to equate to any particular time period if we don't want it to. So let's see here, 1 plus 1 over 365, and then to the 365th power. And we get 2.71456748 I decided to put a bunch of decimal places because I want to show you how this is just getting closer and closer to e, like it does to an asymptote. Like it gets close and close and close to it and never crosses it, and that gives us that value at basically the asymptote. So let's just pick some sort of huge number like 1,000. And I calculated that, and I got 2.71692. So what if we add another 0 on that and do 10,000? That's 10 times as many, right? So 2.71815. Do you see how this now is not, so this jumped from 2 to 2.5 and then 2.25 and then 2.44 and 2.61. It's not changing much anymore, even though when I'm increasing n by a lot. What if we do 100,000? So I am just getting into huge values of n. You could even try something even more insane than that, just to try my theory here. But look at what's happening. This is just converging on this value of e. Try a bigger number and see if you get even closer to this value in your calculator, this 2.718. So see how we're getting really close to that, and it's only going to get closer to this value in our calculator as we use bigger values of n. So I feel like we've proved it to ourselves that this is the number of compoundings getting closer and closer and closer together, and we get this value e so that we don't even have to worry about the number of compoundings anymore. All right, let's use this in a problem. Suppose you invest your first annual bonus of $4,000 in a retirement account, which promises a minimum of 5% interest compounded continuously. Pay attention to that word. How long will it take for this investment to triple in value? Well, this kind of has two different things going on that we should pay attention to. First of all, continuously means we're going to use this formula, right? And then the other thing we should be aware of is we're tripling in value. So even though it has a 4,000, our triple value we would know would be 12,000. I don't think I spelled that right. An extra P. I messed it up. So would be 12,000 to triple it, right? But we don't even really actually need those numbers, because when we plug them in, so we have tripling our money is 12,000, and we're starting with our principal of 4,000, and then we have e to the r, which is 0.05, and we don't know the time because that's what we're trying to find. So how long will it take? We're solving for t. So remember, our first step is that isolation. So if we isolate by dividing out that 4,000, we now have 3. Because 12,000 divided by 4,000 is 3, because how did I get the 12,000 in the first place? I took my principal of 4,000 and I multiplied by 3. So now that I'm isolating and dividing, I get that same number back again. So I really didn't need to take the time to do that. Tripling is going to be a 3, doubling is going to be a 2. It's all about the ratios. All right, so now we get to see something really cool with the fact that our base is e, and this is why base e is on our calculators, because it's so awesome. I am definitely going to do a natural log this time. Don't do a log base 10, because natural log is going to be to your advantage in these problems. So I took the natural log of each side, used that golden rule, our one-to-one property, and now I'm going to use that power property where our exponent goes to the front as a coefficient. So we've got 0.05, which is our rate, times t, which is our time we're solving for, times the natural log of e. Now look how awesome this is. Natural log of e equals 1. Base e to the power of 1 equals e. So 0.05 times t times 1. Look how nice that is. These are so much more simple than the compounding that we just proved. So now we have t equals natural log 3 divided by 0.05. It's basically just the natural log of the ratio, triple, double, whatever the ratio is, divided by the rate as a decimal. That's it. You could like memorize that and not even have to show your work, although I still recommend you show your work, especially on tests, so you can like just verify that you know what you're doing and there's no like question about whether you're cheating or anything. So 21.97 is what I got here, which means it's going to be about 22 years for this to happen. Again, I'm hoping that these numbers are helping you realize that investing money sooner than later to plan for later in life for your retirement is good, because then you can make your money earn money for you instead of just having to earn it all yourself. I wish I'd followed my own advice, even though I knew mathematically that that's what I should be.